I'm Tilman Esslinger, professor at ETH Zurich, and I'm working on quantum simulation with quantum gases. Okay, so what we are doing is we use quantum gases to do what is similar to thermoelectricity, but one could also call it thermomechanics, since in our systems what is transported are atoms and not charges. But the mechanisms and the physics behind it is very related. So what we do in the experiment is we cool a gas of lithium atoms to around 100 nanokelvin, and then we put it into an elongated shaped trap. Then we form this trap such that in the end, with laser beams, in the end you have two traps which are connected with a channel. So two reservoirs and a channel, so very similar to electric conductors. And now we can look at the properties of the transport between those two Fermi fluids. And we can put the Fermi fluid into a superconducting state, so it should be resistance-free, but we ask the question, what is happening when it goes through the channel? And we can, and that only something will flow effectively if we have a difference in chemical potential or a difference in temperature. And in that work you're referring to, we looked at different temperature, how that induced a current. And that is the equivalent of a thermoelectric effect. To trap cold atoms with laser light, the basic idea is that atoms are polarizable objects. So if you shine a laser on it, it will get, you will induce an oscillating dipole moment. And correspondingly, if you have a laser, say, which is retroreflected, has an interference pattern, so maxima and minima, then depending on where the atom sits, at maxima or minima, it will be polarized strong or less strong, and it will experience a force. It's similar to a dipole, an electric dipole in an electric field gradient that also experiences a force. In our case, it's that the dipole is oscillating with the electric field, and that creates you a periodic potential, and you can put ultra cold atoms into this potential, and then you have all the physics of band structures and much more, also interactions which you can tune. Yes, so if you think about a gas of atoms, what can happen? I mean, when you cool it, the atoms get slower, okay. But what else can happen? The thing which characterizes the gas are fluctuations. There can be density fluctuations or phase fluctuations. So we have the atoms behave at these low temperatures as waves. In a Bose-Einstein condensate, they have there are little phase fluctuations. However, when we put the atoms into the optical lattice, you have interactions between the atoms, repulsive interactions, and they reduce. You can get to a state where the density fluctuations are reduced, but phase fluctuations are increased due to a Heisenberg principle. And that's what one calls a quantum phase transition. So it's not a phase transition where you cool something, but you change a parameter. In this case, there's kinetic energy versus interaction energy. If kinetic energy dominates, then you have a Bose-Einstein condensate. If interaction energy dominates, then you have a Mott insulating state. Yeah, that's a very good question. One can ask the question, where in our experience do quantumness play a role? And if you think about it, then it is usually in the fluctuations, in the correlations. If one thing happens here, what happens there? And there are examples where that has a consequence for the overall behavior, and that is, for example, in a superfluid the case. And due to the correlations, say in an electronic superfluid, or also in our case between different spins, because they know of each other, the system flows without resistance. One can ask the question, are there other phenomena? And there the quantum phase transitions are important. They also have a macroscopic consequence. And if you change, as I said earlier, from a phase stable to a phase fluctuating system, so to the Mott insulating phase, the characteristic of these fluctuations at the phase transition, they depend on quantum mechanics. So it is, in a way, a macroscopic quantum effect, because even the macroscopic system will see this characteristic scaling of the correlations. I think the high temperature superconductivity problem is a wonderful problem. It has simple rules, and these rules with which one believes high temperature superconductivity can be explained, these rules can almost be perfectly implemented in cold atoms. It's almost as if the model had been designed for cold atoms, but actually it's the condensed matter physicists who came up with the model. And to understand the understanding of the model, that requires increasingly lower temperatures. The lower you have the temperature, less entropy, the more intriguing we believe the system gets, and we increasingly understand what is happening at the microscopic level with this system. I think it is fantastic work. They have this huge antiferromagnetic crystal, and I see a very interesting prospect for further studies. I think there are a lot of activities, and that's fantastic. We have a very good community. The researchers are open-minded, and they move to interesting questions. And I think a characteristic of the field of cold atoms is that we have many more questions than we can possibly answer. So that makes a very good spirit in this basic research field.